It is my great pleasure to introduce the next panel, the panel on Vision to Reality, Human Exploration of Mars. Kent Rominger is the moderator, and Kent is a naval aviator, an astronaut and shuttle pilot, a veteran of 5 space shuttle missions, 3 of which as pilot, and the last 2 as shuttle commander. In the last decade, Kent Rominger has served at Orbital ATK in various roles, involved with the space launch systems at Orbital ATK. He has been looking at Mars for quite some time, and so eminently suited to lead this panel. Kent, please, the floor is yours.
All sitting down now.
Hey, well, thank you. The rest of the panel is coming out as well, and I want to introduce them, and I'll go from your left to your right, which is my right to my left, on the panelists. And I think if we wind up in the right seats, we have on my far right, your far left, is Patrick Troutman. He graduated in 1984 from Virginia with a Bachelor of Science in Aerospace and Oceanographic Engineering, along with a minor in Computer Science. In the past 30 years, he has worked for NASA, initially performing several space station redesign and risk mitigation studies and leading system analysis related to future space scenarios, including the vision for space exploration, managing the NASA Revolutionary Aerospace Systems Concepts, RASC, program. During the NASA Constellation program, he developed several lunar surface exploration architectures that became the basis of the International Space Exploration Coordination Group, known as ISEG, Lunar Exploration Architecture. Mr. Troutman currently serves as the lead for Human Exploration Architecture Integration for the NASA Human Spaceflight Architecture Team, which is HAT, and as the Human Exploration Strategic Analysis Lead at Langley. His current efforts include defining what the next set of activities for humans should be beyond the International Space Station and how those missions will prepare humanity for an eventual mission to Mars. So thank you for coming, Pat. And by the way, I'm really excited about this panel. You're going to see, by the time I've introduced all the panel members, if you don't know them already, you will see that we have a lot of talent on this panel. To Pat's left is John Baker. John is currently program manager with nearly 30 years of experience at the Jet Propulsion Laboratory in Pasadena, California. John leads the development of both human and robotic exploration system studies and developments. His most recent study, called the Minimal Mars Architecture, has been looking at how to send humans to Mars and return them affordably. Keyword, affordably. John spent many years flying science payloads on the space shuttle, where he saw the value of human spaceflight program and science working together. He also recently led the drop test project to gather water landing loads to support the design of the Orion Crew Module. John supports the Human Spaceflight Architecture Team, Evolvable Mars campaign, and has also supported the Johnson Spaceflight Center on a number of human spaceflight future studies. He was a program executive at NASA headquarters for the successful LRO mission to the moon. Prior to that, he managed the Mars Science Laboratory, Curiosity, rover project systems engineering. John has also led the development of numerous new and innovative hardware technologies, software applications, and mission concepts. His commitment is to see humans working on Mars in his lifetime. I would love to be one of those humans. Okay, next to John is Tony Antonelli. Tony and I go back. We have a history together. Fortunately, it's a good history. But Tony is the Chief Technologist, Exploration Systems for the Civil Space line of business for Lockheed Martin. And in his thought leadership role, he is responsible for helping to synergize and expedite the human exploration strategy through the development and integration of both science objectives and human exploration goals. His efforts contribute to shaping a definitive path for sustainable human missions to Mars. Tony is a retired Navy captain and former NASA astronaut who has accumulated over 4,700 flight hours in over 40 different kinds of aircraft and served as pilot for 2 space shuttle missions, STS-119 and STS-132. While serving at NASA, Tony's leadership roles within the astronaut office included Space Launch System, Commercial Crew, Capsule Communicator, known more as Capcom, and Space Shuttle Propulsion. As the astronaut office lead for Space Shuttle Propulsion, Tony was responsible for all 4 project elements: the external tank, Space Shuttle main engines, solid rocket motors, and solid rocket boosters. In this capacity, he held signature authority for certification of flight readiness while evaluating impacts of various design changes based on ground and in-flight anomalies, obsolescence, and planned upgrades. He earned a Bachelor of Science in Aeronautical Engineering and Astronautical Engineering from Massachusetts Institute of Technology and a Master of Science degree in Aeronautical and Astronautical Engineering from the University of Washington. He is also a distinguished graduate of the U.S. Air Force Test Pilot School. Tony's been honored with numerous awards, including the Defense Superior Medal, Defense Meritorious Service Medal, 2 NASA Spaceflight Medals, a Navy Meritorious Service Medal, NASA Expedition Exceptional Service Medal, and the NASA Return to Flight Award. And lastly and not least is Bret Drake. If you were on the previous panel, you're already very familiar with Bret. Mr. Drake has over 32 years of systems engineering and spaceflight architecture mission design experience, both within the NASA and industry. In his 26 years with NASA, Mr. Drake helped lead the agency in design and analysis of human exploration mission approaches beyond low Earth orbit, including missions to the Moon, near-Earth objects, and Mars. Mr. Drake was the lead architect and author of NASA's Human Exploration of Mars Design Reference Architecture 5.0. He also supported other key strategic planning efforts, including the White House Synthesis Group, Evolvable Mars Campaign, Exploration Systems Architecture Study, and the Review of Human Spaceflight Plans Committee, which is code for the Augustine Committee. Mr. Drake currently works for the Aerospace Corporation, leading the Human Space Architecture Studies. He graduated from the University of Texas at Austin with a Bachelor of Science degree in 1984 with a degree in aerospace engineering. So a round of applause for our panelists. So on this panel, we're going to be a little bit different than some that you've seen because the name of our panel is Vision to Reality. How do we really turn that vision into a reality and go into Mars? And from the introduction of the panelists, you see what kind of background and experience we have on this. I thought it would be great for each of our panelists to take about 10 minutes and give you their thoughts, their approach on that. They've got most of them, some of them have slides to do that. We'll go through each one of them sequentially from your left to right, and then we'll open it up to questions, and hopefully it'll turn into a lot of fun because we could see approaches that are very different. And with that, Pat, I'll turn it over to you.
All right, let's see how the clicker works. One. Oh, that works very good. All right, I have 10 minutes to give you a brief summary of what the Evolvable Mars campaign is and how we think we can make things more affordable and sustainable. The EMC is a study activity. The journey to Mars is the plan in a sense. So we're a system study that's looking at various options of achieving the journey to Mars. We take a lot of input from past studies, ongoing studies. John's going to tell you about one that we folded into the analysis to take a look at. So our job is to help inform the decision makers on what investments to make near term to enable a variety of futures. The name's really key, Evolvable Mars Campaign, because it has to evolve based upon discovery, technology, progress, and politics. And those are always changing. So anything you see today is probably not what you're going to see 20 years from now. But what you will see is a methodology, is an approach, is a philosophy for enabling sustained exploration of Mars. Now, being from NASA, they like to make charts. This chart started out 2 years ago, and it started off as the guiding principles for the Evolvable Mars campaign. I have put it on the wall in my office, all the various iterations. It started off with like 5 bullets. So I'm not going to read the bullets here because that would take the remainder of my 10 minutes. Bottom line is it's got to fit within a reasonable budget. Number 2, no gaps in activity. As Andy Weir said the other day, you don't want to put the book down. It's got to be like a good movie. It's got to be exciting, compelling, and people want to keep seeing it going on. So that's what the campaign aspect is. So no gaps. No stunts. Everything we do in the Evolvable Mars campaign builds into something better. We don't have any offshoots where we're just going to do something that doesn't add to the value of the campaign and lead towards the next mission. And then the one that really sort of stays on here, and I'm going to talk more about, is the resiliency, the refurbishing, the reusability aspects. This was a going-in assumption because we have sustainable transportation systems here on Earth. We don't throw everything away each time. So you're going to see a lot of systems repurposed, reused, and refueled in the architecture. And the bottom line is cooperation and partnering. We want to build in hooks. Depending on who's doing well, what international partners come to the table, so that we can accommodate all that and build a better whole from it. So you've seen a lot of this aspect today here. You heard about the Earth independent and the proving ground and the Earth independent. Truth is from an operational standpoint, we're going to be Earth independent. But when we get to Mars, we're still bringing almost everything we need with us except for some propellant initially. So we really don't achieve Earth independence till we've been on Mars for a decade or so. But I've also broken that Earth independent phase into 2 blocks, because each one of these blocks that you see on this chart here represent a major investment. Of course, Sam just talked about space station and all it's doing for exploration to future destinations. We also talked a little bit about the proving ground. But to go from space station to the proving ground, that requires going from the space station investment to the SLS Orion investment, and perhaps the initial cislunar habitat. The next big investment after that gets us to the Mars system. That's the in-space transportation, and that's the 1,000-day, highly reliable, lightweight habitation class systems we need for Mars. Then the next big chunk of investment is going down to the surface of Mars. That's the landers, that's the ISRU, that's the fission power plants, that's the long-duration surface systems. So if you look at these boxes, they're sort of like natural pause points in what could be a sequence of events which creates the Evolvable Mars campaign. But we can't move on to the next phase until we've made the investments for the current phase and demonstrated that they work well. So a couple of things from the Evolvable Mars campaign. Here's some samples of some spaceships we've looked at. For comparison purposes, I took the nuclear thermal rocket from one of Bret's architectures, which was for a crew of 6. The Evolvable Mars campaign is for a crew of 4. And so the 2 driving things we have is we've gone down to a crew of 4. Doesn't mean we can't have more than 4 in space at any one time. And the other thing, we're governed by the rate of SLS launch rates. So we've been told that SLS will get to 2 launches a year, maybe a surge to 3. It takes about 8 launches to make these architectures work of the SLS, depending on what performance numbers you use. That says we can only go every other opportunity. So 4 years, 8 launches. So the EMC is scheduled upon that cadence. So there's a series of missions, 8 SLS launches, each one interesting and fascinating by itself, strung together to enable a single Mars mission. Looking at these 2 concepts up top, 2 of our points of comparisons that we're working right now. On the right is a locksmithing stage with solar electric propulsion pre-deployment of systems. Very traditional for the piloted aspect of it, where you use chemical to get them out there. You meet in Mars orbit, you meet your return propellant, and they come back. The one on the left is where we've taken the reusability and refueling up a notch. That's what we call the hybrid propulsion system. That truly is a spaceship because it starts from cislunar space, it goes to the Mars system, it doesn't have to refuel, it doesn't have to resupply, and it turns around and comes back to cislunar space where it's refueled and refurbished again. So with a combination of high-power solar electric propulsion and some small chemical thrusters, we can actually go from sphere of influence of the Earth-Moon to sphere of influence of Mars and back with that particular concept. So let's talk about affordability and sustainability. Oh, that's a cool transition. Talked about the reusability a lot. First of all, is we need to reuse, repurpose ISX to the maximum extent possible. Sam talked about what a fantastic platform is for doing this long-duration research. There's no need to replicate it in cislunar space. We should be building in cislunar space the actual Mars systems that will take us to Mars. So let's use SLS where it is right now for everything we can, and use cislunar space for those things like our unique environment, like radiation or dormancy periods. So we should be using ISS and actually doing many Mars analogs on ISS. We're going to use an evolution of the asteroid redirect vehicle in our configuration, in our solar electric propulsion systems. That system has a net 50 kilowatts on the solar arrays. We're going to up that, close to, by the time you get to the Mars power, we're going to have 300 kilowatts running through the bus to make these systems work, these reusable hybrid systems work. But the components, the technology, the thrusters, all can be used armed systems. We just have to gang them up a little bit, even the tanks. It's probably not the most efficient way to do it, and probably 10 years from now, if we actually design this thing, it would probably be more unique rather than totally looking like ARM. Reuse of infrastructure for multiple missions. You see two paths on there. The little path next to the bottom is what we call the small habitat class. We had the Orion folks talk earlier about how the Orion systems and maybe in the Orion itself could be used in the Mars mission architecture as we launch cislunar space. Those short systems are required that house a crew for a matter of days to weeks. Mostly open systems, rad-hard electronics. We need to see those things in other systems in the architecture, like landers, like taxis, like excursion vehicles. Same thing with the large habitats. There's 1,000-day class habitat for a crew of 4. Those can be used for transit, for on the surface of Phobos, and for on the surface of Mars, again, with some adjustments and capabilities and outfitting. So here's a little more example of the small habitat commonality we've been looking at. You look at the little green circles in each one of these blobs, and it's a function. It's that small cabin function, that small short duration system functions that are good for any of these particular missions. And those all could be derived from Orion systems. One of the things I want to point out is even though we talk about we have a crew of 4 Mars missions, because we're going every other opportunity, every 4 years to the Mars system, there are times in between while the crew is going to Mars where we can actually send a crew to cislunar space. So in the Volatile Mars campaign, we keep a very small station in cislunar space. Station's a bad word. Let's call it something to dock to, a docking port. Crew can visit that on Orion while we have crew on the way to Mars or on Mars. So we have 8 people in space at once. And of course, we have robotic crew members, so some nations and companies can have robotic crew members on this too. And so that's where the commercial and international participation comes in, because in some of these architectures, certainly all the habitats are reusable in architecture, so because they come back to cislunar space, but they can be provisioned by commercial international vehicles. And with the hybrid option, we actually have refueling of xenon and hypergal's or LOX methane. That could be accomplished by commercial launch vehicles also. So even though we're limited to 2 SLSs a year, because we can involve the internationals and new commercials for refueling, we can actually get more activity going on in the architecture. So I'm going to close with this because I'm pretty close to my 10 minutes, I imagine.
Yes, you
are. So I paid $29 for the right to this chart, so I wanted to use it. I want to give Bret credit here. Bret designed an incredible architecture that was driven by science that achieved the most human-enabled science practicable over multiple sites. But it was a beast to feed. Very strong, very capable, but we couldn't handle the surge rate. We couldn't handle throwing away each of the outpost sites and moving on to a new one. So what the EMC tried to do, our point of departure, is try to slim it down a little bit. We go back to the same site over and over again. That's also the work to science, but also because the theme of the EMC is human settlement beyond, or not settlement, sustained human presence beyond low Earth orbit. Freudian slip. So he's a little more slim, a little easier to keep. However, even that is going to be a challenge with our current budget profile. So we're looking at something called the progressive development option, which looks more like a marathon runner, a little slimmer, and it was partly inspired by some of the work that John Baker and JPL had done, cutting back on things. We reduced some upfront costs, we reduced some capability development needs initially, we reduced some mission content, but we ended up with something that can actually grow to the POD, the big EMC. So I think what John's going to show you is in between the flyby and the EMC PDO. But the attempt is, we don't want the last one on the left, because I call that a stunt. If it's the exact same transportation system and habitation systems, then it's a shakedown cruise, and that's great. But if you're doing unique systems just to do a flyby to check a box early on, I don't think that's in the way of doing good for the EMC. So I think I'm at my limit. I will close with that. Thank you.
Great, thank you. That was great.
Well, good afternoon. It's great to be here with you. Oh, and I got too fast. I'm going to show you the exact same chart but I'm going to say something different about this chart. This is actually a photorealistic view of if you were standing on Phobos, what Mars would look like. And it's pretty close and pretty accurate based on all the scientific knowledge we have of Phobos at this point. And the whole point of this particular panel was how do we make this real? And I would like for all of you to be sitting in your chair, thinking for yourself, how do we make this real? How do we one day put humans on Mars? So you may be listening to my talking, and I may have a few things to say, but please, I encourage you to be thinking in your own chair and asking yourself that question. I promise you that what I'm going to tell you isn't the answer. We have given it a fair amount of thought, but there's ways to go. So there are a couple of ways to look at this. Pat talked a lot about the technical architectures. I'm going to talk a little bit about the programmatic aspects of how do you make something real and actually move it forward. And the challenges here are really quite delicate. I mean, you're talking about a very sophisticated balancing act where you're trying to balance technical feasibility, fiscal affordability, stakeholders' interest horizon. I mean, you know for yourself that if you're saving to buy your next car and you're not going to have that car for 30 or 40 years, like, wow, is it really worth it? But if you can save for that car and you can get it in the next 5 or 10 years, like, okay, yeah, I'm going to do that. So think for yourself that literally if we said we're not going to Mars until 2050, okay, this is great, but what are we doing, right? So we actually took that to heart and decided that the 2030s at the latest would be a reasonable stakeholder interest horizon, something in our time frame where you actually know where you're going to be at that time. Acceptable risk. We've heard a lot about that. There's been a lot of great work done, and we think that risk is a very clear variable in what you're doing, and we actually designed in our architecture how you mitigate some of those risks. You've heard a lot of discussion about flying the systems, and we test all of our systems in cislunar space as a part of the architecture that we put together. International and private sector engagement, again, a key piece of we're probably not going to do this alone. And then finally, how do you actually take a 25 or 30-year program which is going to cover 7 different possible administrations and keep them engaged and realized. So I'm going to say what our thoughts are on this particular matter. So for the technical feasibility, when we actually did our study, we looked at technology that was ready now or soon, or you absolutely had to have, like regenerative life support systems. And we started with that study. That also allows you to keep the cost down, but it also allows you to on-ramp technologies when they're truly ready, when you've actually done the investment and the qualification in order to use them properly. For fiscal affordability, I have a feeling it's, there we go. We took the approach of using limited or common elements. So you've talked about the 6 or 7 or 8 pieces of an architecture. We stuck with 6. SLS, Orion, a deep space hab, a Mars lander, and then finally we used a chemical prop stage to kind of as the glue to adjust all of the different energy requirements and make the architecture hang together. And by the way, my colleague here, Hoppy Price, was key to putting that all together. If you have more questions about that, feel free to talk to him as well. Stakeholder interest horizon. Let's see if this is going to click or not. There we go. Land in the 2030s. It's 2016 now. Where will you be 20 years from now? You're planning on being around, I'm sure. So you know that you want to see it, and at least I know I want to see humans walk on Mars in my lifetime. Risk. Test systems incrementally. Make sure they work out. We've heard from the previous panel about testing things out in cislunar space. Again, you do incremental buildup of capability. Pat said the same thing. I think there's a lot of agreement in that particular arena. For international and private sector engagement, create alignment early. I think these kinds of events are wonderful for getting people together, sharing your thoughts and ideas. You know, where there's commonality or where there's alignment, great, and where there isn't, I think that's an opportunity for people to get together and bring their thinking together and really kind of hammer out what needs to happen. So one such example would be in situ resource utilization. We've heard lots of different opinions about that. What do we want to do? How do we engage the private sector? How do we engage the international sector? Who's going to build what and when? And then how do all these different groups participate? And then finally, political realism. How do you manage to deal with lots of different administrations over a long period of time? I think there are two things that I've heard from previous speakers. One is you want to demonstrate progress. So you want a series of missions, not just one big mission that gets you there. And because if you have a series of missions, and by the way, this feeds nicely into fiscal affordability, it feeds nicely into dealing with risk, that you can incrementally test systems out and build things up over time. I think that's a sound approach for not only developing and managing things, but also to keeping people engaged in what you're doing. And then, and I think that's really important. And then also, I think you want to demonstrate relevance, like why are you doing what you're doing? And I think we've had a lot of discussions about why Mars. Every one of us has their own reason for it. They're all the right reasons. We should keep going with them. So this is the one of the architecture charts. So we put this JPL minimal Mars architecture together for a reason, to show that there was an existence proof that it was possible to send humans to Mars and have it be affordable. But to do that, we had to build our own architecture, and we used a lot of the existing elements that NASA or industry or other people were already thinking about, and we architected them in a way. And this shows the Phobos mission architecture in 4 not-so-easy SLS launches. We actually we use SEP tugs to deploy a habitat to Phobos and the return propellant, as well as a TEI stage. And then we launched the crew, we launched a deep space habitat and the crew to Mars. They rendezvous down on the surface of Phobos, come back home, or come back through Deimos and then fly home in their habitat. And that's just one example. There's actually a detailed paper available. You can read more about it in the Humans to Mars report, which is in your packet. I encourage you to definitely read it. By the way, we also added landers. So I'm talking about the things you have to have, which are part of a plan. And so you saw an architecture. Now I'm going to show you what we used as a manifest, from the initial SLS test flights on the top row to the second row of test flights in the proving ground. And by the way, we got some great feedback. We actually heard from people. They said, you know what? And this feeds to another point. They didn't like one particular part of this architecture. They didn't like the fact that there was a flight gap between after the ISS ended in 28 and when we actually sent crews to Mars in 33. So we added what are reasonably probably a couple of new missions in cislunar space to continue working out all of the gaps and the bugs and all of the different things you need to do to actually send humans to the surface. And then finally, and that's really important, by the way, is to be able to listen and accept feedback and adjust and adapt to what people are telling you. The third row becomes the first mission to Phobos and to the Mars system. And this is the 4-launch architecture I just showed you. And we actually put this together in reasonable time frames and work things out. The SEP tugs allow you to a lot more launch flexibility. You can pre-deploy things years in advance. That keeps people interested and engaged, because now you're launching crew to the system and you already have habitats there. You already have stockpiles of food and fuel that are ready for them when they get there. And then they can make a relatively fast transit using standard propulsion technologies in a habitat that gets them to Mars. And then finally, the 4th row is when we actually do the first mission to the surface. It takes a couple of more launches, similar to what we do with Phobos, to actually send this relatively good-sized lander to Mars. And that in our particular version of the architecture, we send 2 crew down to the surface for, I think, about 3 or 4 weeks, and then bring them back up, and then with the crew come home after that. So this is just an example of, and we're welcome to ideas, and we in fact would encourage you to build off of it. It's great to hear that NASA and the Evolvable Mars campaign are actually doing that. So another critical piece of a plan, and then finally, you integrate all these things together into a cost, and this is how you really assess the feasibility of an architecture, is by looking at, does it actually fit? And so we made a fairly reasonable assumption that the NASA human spaceflight budget would increase with inflation every year, and so far that's been pretty close in the last year or two, and you can see kind of how these, what they call the sand chart, how these cost numbers lay out over time. The peaks and valleys, by the way, we didn't make any effort to smooth things out. And by the way, this cost was actually done by Aerospace. It's good to have an independent group do your cost estimating for you so that there's no, because people who do concept work sometimes get attached to making sure their concepts are affordable. So you want to have an independent group be looking at this independently and working with you. But by the way, we made no attempt to kind of smooth out the dips and the peaks and the valleys. If and when a program goes forward, there would be much more detailed planning to do all that and to make things more realistic. But this particular architecture, as you can see, comes pretty close to fitting in to an adjusted budget for inflation. Takes the ISS all to 2028 and basically allows you to go to Phobos in 33, a short stay to Mars in 39, and finally a long stay for 1.5 years in 43. So just with that, I think that with a plan, in order to make anything real, you have to have a plan. In order to have a plan, you have to have the who, what, when, where, why, how. And really, even before that, you really need a coherent long-term strategy, something greater than 5 years that can be articulated. And I think that's really incumbent on NASA to do that. I think that's about my 10 minutes.
Great. Thank you.
All right. Nice job. All right, thanks. I'm excited to be here. It was interesting to hear Pat and John's take. A lot of that is out there and published. I kind of approach the idea of vision to reality from a different, higher systems engineering perspective that said, hey, what can you get done in 10 years? It has to be affordable. So now just make it fit. What can you accomplish? So that was the starting point. The mission, bold and achievable to get humans in Mars orbit. Our phrase for that from our early career folks is Mars Base Camp, with the idea that you're staging things in Mars orbit with an eventual kind of summit, if you will, of putting humans down on the surface of Mars. Transport scientist astronauts from Earth to the moons of Mars to answer fundamental science questions and then prepare for an eventual human landing on the surface of Mars. If you caught the previous discussion about latency from the earlier panel, for us, the key is putting the scientists, so now making science decisions in real time from Mars orbit. We think that's a key part of taking advantage of the proximity to the rovers, and we'll talk more about that. From a key stakeholder interest perspective, we start in the bottom left with the Exploration Mission 1. Be the second flight of Orion, set a distance record for human-rated spacecraft as it goes out past the moon. Be the first test flight of SLS, and then up through the EM2, accomplishing the proving ground flight test objectives that you've heard NASA brief, and then on to the same shakedown cruise in cislunar space, testing out all of your systems before you send humans all the way on the journey to Mars. In addition, There's a cadence perspective. I think John was hinting at the exact same thing. There has to be engagement in the process. I'll show you about a 40-second video that stitches all of these elements together. Okay, so a key part of turning the vision into a reality and accomplishing stuff in relatively short term, something bold but exciting, is leveraging your existing capabilities. So, using the capabilities of SLS to launch Orion and co-manifested payloads into cislunar space. And then using Orion, designed from the ground up to do deep space human exploration, and using that capability throughout the architecture. So crew safety, redundancy from an avionics standpoint, radiation protection, both from radiation-hardened avionics and also storm shelter for the crew. And in addition to that, from Mars orbit, being the command and control, and I think Pat was talking about an excursion vehicle. Everything that you need in an excursion vehicle exists, if you will, inside of Orion. So now it's taking the capabilities that you've already invested in and tested and using those for multiple missions, not unlike the small habitat commonality theme. If you notice, there's a symmetry about this architecture. There's two Orions. There's a habitat and a laboratory that are similar. There's crew quarters with the idea that you can drive affordability with the same commonality themes that were in the small habitat presentation. And then the inset is similar from the previous presentations, is forward deploy mission critical assets using solar electric propulsion into Mars orbit. And then we constrain the team to say, look, it's nothing that crew health and safety depends on can be forward deployed. You need to keep that with you as critical stuff. But anything that you can write off as mission critical but not safety critical, then you can forward deploy. And then it's why are you going and what you can accomplish from Mars orbit. And this is human excursions to the Martian moons. The idea is working to answer the big three science questions of where do we come from, where are we going, and are we alone? Laboratory equipment, one of the advantages of forward deploying this with solar electric propulsion, a laboratory is while you have that electrical power to run the thrusters while you're transiting to Mars orbit, once you get there, now you have this electrical power that you don't need to power the thrusters, and now you can power the equipment inside the laboratory. There's a persistence element in addition to the low latency. So if you have scientists there with low latency access to rovers, and our Skunkworks guys have designed, this UAV was specifically designed for the Martian atmosphere. If you have them with low latency capability to make real-time decisions, take advantage of all the flexibility that humans bring, and have the persistence to modify. I think somebody said not to use the word scripted before. So come up with the plan while you're there, learn from a particular operation, and then be there again tomorrow to take advantage of that knowledge. Additionally, the previous group talked about a rover, so we're not imagining kind of a one at a time. Imagine if you were the scientist inside the laboratory driving the Curiosity rover and there was something really interesting but kind of close to the cliff. I mean, do you want to be the scientist that makes the mistake that ends that rover? So we're imagining taking advantage of micro electronic mechanical systems, hoppers and UAVs, and having access to, by forward deploying mission critical cargo with SEP. You're really limited by just what you can package and send on your way there. But having access, global access to the surface of Mars and being able to accomplish we think more science in months than we've been able to accomplish from the way we do telerobotics today to the surface of the moon that we've been doing for 40 years. Again, to make it reality, it's got to be things that exist. There's no magic here on the list. All these things exist, are currently in development. In addition, it's a bold, big mission, so there's room for all kinds of participation, international participation from an element standpoint to an experiment to a astronaut or cosmonaut, and then the same with public and private partnerships that feed into this in all kinds of various ways. This is just another way to show the summary of the video. The key piece for me on this chart is the part across the bottom, which is just as important to making this reality, which is a public focus, right? You've got to have something, we think, every year to keep the public engaged in any kind of mission spanning this duration. And then real quick, Lockheed Martin, as Rommel said in the intro, so I got to articulate the fact that we're taking advantage of Orion's capability, deep space operations, layers of redundancy, long duration capability from a spacecraft standpoint, and also the thermal protection system so that you can, humans can re-enter to Earth safely. We see a lot of uses of this capability throughout the architecture, and taking advantage of those is what's going to turn this vision into reality. And then just the obligatory find more information on the internet slide.
Okay, thanks.
All right, so I wanted to, purpose of this panel was turning the vision into reality. So I wanted to step back, and I'm not going to talk architectures, but instead I wanted to step back and say, all right, from what I've experienced working both in industry and within the agency, what are some of the key features? What are some of the things that we as a community can do to help move this vision of human exploration of Mars forward? If you look back the last couple of decades, there have been a lot of studies. There have been a lot of blue ribbon commissions. There have been a lot of strategic plans. And every time there was a shuttle accident, there was a reevaluation of what are we doing? Why are we in space? What should we be doing as humanity in terms of exploration? And we keep coming back to that premise of expanding human presence for longer durations and longer distance, and that's kind of the goal of what the human spaceflight program should be. It continuously comes up, it continuously is reconfirmed. You look at the authorization acts of 2005 and 8 and 10, and they continue to reconfirm that we as a nation want to be the leaders in expanding human presence beyond low Earth orbit. And Mars is generally that goal that's always held out there as the goal that we should be driving towards. I don't like that term of horizon goal because the horizon is always in the distance and you never get there. So it is a goal that we all want to achieve. And so we need to keep an eye on that. And also, as all the discussions have gone on the last couple of days, and will continue tomorrow, human exploration of Mars is a is a multi-administration, a multi-Congress endeavor. And so what we put together has to be sustainable from a political perspective, just like John and Pat and Tony have been talking about. So we've got to construct the why we're doing this, construct the architecture that the stakeholders can actually relate to help make it a sustainable program. But one thing, yeah, there have been a lot of studies, and we get a lot of grief over it's nothing but paper, a lot of studies. But coming out of those studies, there's a lot of common things that always come to the top. For these Mars missions, there are key capabilities that are consistent across all of these architectures. No matter what pathway you talk about, if you talk about Phobos missions, if you talk about short stay, Phobos, short stay, long stay, or the EMC evolvable campaign, these key capabilities always are fundamental to human exploration of Mars. 1,000-day missions. If you try to push it shorter, then you require a lot more propulsion capability, a lot more transportation. Becomes much more difficult. So we revolve around 1,000-day class missions, 300 to 500 days at Mars. We got to deal with the comm delays. That's a given, so we must do that. High robust power systems is important for all these architectures. Ability to land large payloads on the surface of Mars. If we want to go to the surface, which we all do, that is a key capability that we've got to accomplish. Get from the 1 ton that we can do today up to 20 to 30 tons in the future. A lot of talk about being able to live off the land, to cut the logistics supply, so in-situ resource utilization. Use the atmosphere, use perhaps the ice, water on the surface to enable that exploration capability. Helps with that sustainability aspect. When we're there, we want to be able to rove long distances. The previous panel talked about getting out and moving around. We want to be able to go to those exciting places. We're going to land in a safe place, which is going to be geologically boring, but we want to go to exciting locations, which are going to be a rove away. And being able to enable that routine global exploration, or regional exploration is important. And then Orion, as Tony just talked about, is a key capability, being able to return from lunar distances, perhaps Mars distances, Mars re-entries is important. And having a capability for all these missions, supporting the crews for these long durations, you got to take all your food, your life support, everything with you, requires a lot of mass. And in order to keep the number of launches reasonable, having a heavy lift launch vehicle as the initial starting point for all these architectures is important. So keeping our eye on all those capabilities is one of the key aspects. There's accompanying all those is the key technology suite that's important for these missions. And again, through all these studies and all these pathways and all these blue ribbon committees, the same sort of technologies always are on the list. And just for grins, I went back and looked at the White House synthesis group done in the 1990s. And what are page 6 of their report, what are the key technologies and how does that compare to what's in the Evolvable Mars campaign today? And the list is the same. The only few changes I've noted there, instead of a 150-ton metric ton launch vehicle, we're talking 130 metric ton. Instead of nuclear electric propulsion, nuclear thermal propulsion, we're talking solar electric propulsion. But they're all the same. So what we need to do to turn this vision into an actual reality is focus on these key technologies and advance them. We need to increase the pace. 2030 is not that far away. There's not a lot of time to develop those technologies, get them in place, prove them, and move on. So focus on the key technologies. There have also been a lot of disruptive technologies. People throw out wild ideas, like tethers or mag launches or power beaming and all these different types of things. And while they have a lot of good interest, they're not the core technologies. None of them have proven to be those revolutionary silver bullet that will solve all the problems. So again, focusing on those core technologies, increasing the pace of development of those is important. Another thing to keep note, you saw in each one of these architectures that human exploration of Mars is a complex system-to-system problem. Apollo was complex with a launch vehicle, command module, service module, a lunar descent stage, a lunar ascent stage, rovers. Take that and now multiply it by even more for our Mars mission. So we as a community, when we see chatter, we see discussions about a revolutionary new type of launch vehicle or a new in-space transportation system, you have to put that in a system-to-system architecture context. We play the game of whack-a-mole. If you change one piece of the architecture, it ripples through all the others. And it's generally not a zero-sum game. It changes a lot of the pieces of the architecture, and you have to keep an eye on those pieces if you want to change one aspect. So as different architectural concepts are brought up, ask yourself, how does that fit in to the total system-of-system architecture. How does what one change in this one small piece of the architecture ripple through other pieces? Does it cut off complete pieces of the architecture which may not make those actually viable? So it's a big system-of-systems problem. I'm glad to see John and Pat and Tony all talked about risk and making risk reasonable. We have an active voice in doing that. In fact, the public is not risk adverse. The public often takes risk. I mean, you got a little comparison right there of explorers who try to accomplish the feat of topping Mount Everest. And if you look at the success rate, it's about 27% of the people actually achieve it, but the fatality rate is about 1.7%. Compare that to the shuttle, success rate of about 98%, and the same sort of a fatality rate. But yet, if you look in the press, it's often an aviation accident or a climbing accident, but it's a shuttle disaster. And so how we articulate the risk and how we characterize it is important in order to move this forward. We can't focus solely on risk because risk can be paralyzing. It'll keep us from going. And how we articulate that narrative is important. I really like what JPL did with the Mars Science Laboratory. When it was landing, I mean, it's a piece of metal. I mean, it was just circuit boards and metal, and no one was on board, but they characterized it as the 7 minutes of terror. And the public could resonate with that, and they could actually it helped them live through that experience, and they became part of it. So we need to be an active voice in helping translate our experience, our adventure, and the risks that the crews are taking, but making it reasonable. Robotic missions paved the way. There's been a lot of discussion about gap-filling activities and how the robotic missions fit in, and we need to continue that. They also can help us buy down risk. But you also have to keep in mind that 2030s is not that far along, and it takes time to develop a Mars system, fly it, test it, see how it operates before you can fold it into the next mission. So, yes, testing with those robotic missions is important, but there's not a lot of time between now and when we need to fly to Mars. On the affordability and sustainability front, often we hit this conflict that an affordable architecture, one that really costs very little, can actually not be sustainable. It can be viewed as a flash in the pan, a stunt, and it won't have the legs to sustain itself for long periods of time. So we all know that NASA's budget has eroded. We all know that we've got challenges from a funding perspective. But consistent with that, changing the narrative from a risk perspective, if we can do a better job of explaining why it's important to spend money on space. We don't spend money in space. We spend money here on the Earth for space. And if we can help change that dialogue and the why we're doing this and how it impacts everybody's lives, hopefully we can change the priority of where NASA sits in terms of the federal budget. So understanding that cost aspect, putting an architecture in place that is sustainable, so one that has legs to live for a long period of time. It's not just necessarily the cheapest one. Is a very difficult challenge that we all must face. And then lastly, I want to hit on is, the journey to Mars, the plan. And NASA gets beat up, they're kind of stuck between a rock and a hard place, because if right now they're being criticized, well, they don't have a plan. We don't see what all the systems are or when it's going to happen and what are all the specifications for it. But in reality, you look at those constraints of how much money we have, the time, and really what it takes to do this job, it's an over-constrained problem. And if NASA spelled out exactly what's going to happen between now and the next 20 years, because it'll, given all that has to be developed, it's going to take 15 to 20 years to develop all those systems. If they laid all that out right now, it would be wrong. I mean, every aspect of it would be wrong. Think about your phone and what you have in your computing systems. If you specified that 15, 20 years ago, you'd be wrong. So NASA faces that same problem. And a good example of that is when we did Design Reference Architecture 5, we got all the propulsion concept experts across the nation, sat them in a room, what's the current state of each one of these technologies, walk through all of them, which ones should we look at, and the teams concluded that nuclear thermal propulsion and advanced chemical were the leading contenders, so let's use those as the references. Again, as a reference, it was not, it's not NASA's plan, but it was, based on what we know today. Electric propulsion, nuclear and solar, were felt by the experts at the time to be not there yet. They needed more time to develop. So they were put in the emerging technology category. Fast forward 8 years now, solar electric propulsion has made a lot of advancement. You see it on ComSats today. It's flying routinely. And so it has advanced to the point where it is now mainstream. And so if we specified 8 years ago, this is exactly what the plan is going to be, it would have been wrong. So yeah, we need a plan, but the plan should be more of use this vision of what we want to do from a human exploration perspective, and then back off of that. What do we do in the next 5 or 10 years along that path? What are the key critical things that we need to do, like Orion, SLS ground ops, those initial missions in cislunar space? And let the farther right side of the equation, what we do at Mars, evolve as we go along. And that's, I think, how we would help turn this vision into reality.
Great.
That's it.
All right, thank you. Okay, so now we want to have questions and discussion, and I want to ask the first question. And actually, I want to ask the audience and the panel members both this by a show of hands.
Uh-oh, a loaded question. Here it comes.
So it is. I'm stepping out here so I can see the audience out of the lights. But we're all about putting humans on Mars, exploring Mars. We want to do that safely. As I see this plan rolled out, we're going into the vicinity of the moon, cislunar. So how many in this room believe that we can safely explore Mars without sending humans to the surface of the moon first? Okay, that's pretty good.
Without?
You said safely, so that's all your definition of what is safe.
Safely, yeah. Okay, so now let me flip that question a little bit. How many think when we're in cislunar, because we're going to spend maybe a couple decades in cislunar orbit on our way to Mars, how many think it would be smart to send humans to the surface of the moon to mitigate some of the risks going to Mars? How many think that? So yeah, not quite as many hands, and on our panel.
Well, it depends who pays for it. That's
What's that?
It depends on who pays for it. If the partners were going to do it, my hand's way up. If I have to pay for that, but delay going to Mars,
Right.
I'm not going to do that.
Right. So I think if our goal is to put humans on Mars, if we send humans to the surface of the moon, how long, John, I'm looking at you.
Yeah.
How long does that delay or push us putting humans on Mars if we did that?
Well, we actually included a single test flight to the surface of the moon to test the guidance and control and all the propulsion and crew systems. But a single flight doesn't delay you. And in fact, it gives you more confidence because you're much closer to Earth. You can abort back to existing assets in cislunar space if there's a problem. But if you,
And that flight has humans on it?
What's that?
And that flight does have humans
Yeah.
on board?
Yeah, a short mission to the surface with 2 crew. But if you spend more than a year, I think I had 5 test flights. If you do more than about 4 or 5 test flights to cislunar space, I think it becomes difficult to justify. And I think it also becomes, justify meaning convince Congress and other stakeholders that you really need to be spending that much time there and there's a whole lot more to do. And if you do more than that, then you really are going to push it into the 40s and 50s, and I think you'll lose a lot of people's interest.
So Ken, in the second Augustine committee, we had that discussion. What do you do? How does a lunar mission fit in terms of reducing the risk for Mars missions? And we polled all the subject matter experts and said, okay, for your system, what do you learn by going to the moon? How does it help buy down risk? And in every case, every single person that came back said, well, if humans are involved and I'm testing at the moon with humans, I've got to go through all the certification, all the verification to make sure that I don't kill the crew on the lunar mission, that I'm struggling what I would actually gain in terms of just going to Mars. And the only thing that you can come back to gets back to the system-to-system issues, that you can't test the systems together on the Earth because they're just so complex, you just can't do it. So the system-to-system, how things operate together. and the unknown unknowns, that just putting it in space for long periods of time in a more relevant environment that you may not be able to replicate. You didn't think about it or couldn't replicate it on the ground. So you have to break those components back and say, all right, given all of that, how does it fit into the affordability and the time frame perspective?
Bringing it back to reality, and Bret was hitting on at this at the end of his remarks, is we laid out this vision that spans, all the way out to the humans on the surface of Mars, but then zeroing back in and detailed work and focus on what we're doing. So the test flights of SLS, the next 2 flights of Orion, the building the cislunar deep space habitation capability, really is the right, and I realize this is the Human to Mars conference, so any of the other destinations, but imagine if we learned something in the next 5 years that said, whoa, we really need to send humans to, somewhere else. Maybe it's, Earth, Sun, L1 to build a telescope because there's something we absolutely have to look at with a telescope that we can't launch in a single launch, or I don't know, you could come up with there's already a bunch of other destinations of where folks want to go, so I was just throwing that out there. But the beauty of this is, and all of us had the things we're doing now are the right things to do, whether you end up wanting to buy down risk by going to the surface of the moon or not.
Great. And Pat, I think you're the only one that hadn't gotten to talk about this.
Well, okay, so it doesn't matter whether we're in NASA or government or people. Once we build something, once we invest in it, we tend to want to hang on to it. Does everyone have a garage full of stuff? We have a garage full of stuff. You have to get rid of some of the clutter so you can move on to do something else. So every time we go to another destination, we build more infrastructure, we want to maintain it. It's part of the political, bureaucratic process. So you want to make sure that you are streamlined as possible in the first place. And this is what I'm not calling going to the moon a stunt, but I'm saying things that aren't on the direct path to what your goal is. A campaign is a series of missions to achieve an ultimate goal. And if those missions are sort of on the side and they're not laying 100% towards that ultimate goal, or they're taking away from that, it becomes more of a distraction than progress on the goal. Now, I'll admit it, I'm a lunar guy, okay? If you ask the question, should we go to the moon or Mars? I would say the moon. My job is to get us to Mars, all right? So if you want to go to Mars, don't go to the moon.
Great. Hey, so with that, I would love to hear from the audience and love to hear what's on your mind. Questions? Yes.
Yes, hi. Creighton Jones with Future Science. So a lot has been made about the recent mission of Scott Kelly and his successful return, and it's been sort of put forward as proof that man can exist in space for a year. But himself, in interviews, has sort of pushed the point that, from his perspective, it'd be great if we could do this mission a lot quicker in terms of getting to Mars. And it seems that at present, as far as the technologies we know can be developed, to get the kind of thrust and specific impulse to cut that time down to a fraction of current estimates, it's nuclear thermal. So my question is, how much is being done on developing and looking at nuclear thermal still, and what are the roadblocks to it becoming a real viable alternative?
Can I take that first?
You bet.
All right, so there's still basic physics. If we're doing a conjunction class mission, you can only push it so far, else the power and the thrust gets well beyond our current concepts for nuclear thermal. Part of that is making the crude part of it very quickly, and then if you get to the Mars gravity well very quickly and down to the surface, you get these windows of 180 one-year type travel things. But if we talk about an orbital mission, you're still in space for 1,000 days. And if you push it with nuclear thermal without incredible advances in technology, gigawatt nuclear tower plants, this big for an NEP or super high thrust, you're just not going to get there. There are select opportunities where you can make, months happen with incredible thrust and incredible power. But the bottom line is what we really need to answer the question is, not can we get anywhere faster, because Mars is just one stop on the way to other places. The real question is can we do extended space travel without artificial gravity? And to me, one of the great reasons for space station is to answer that problem. So yes, we had 1 year, Scott Kelly, we had an unfortunate Russian citizen who was there during the Mir during regime change. Those are the only 2 people on planet Earth that have up to a year or a little bit more in space. We need more time on people, more people on time in space on the space station before it gets transitioned to whatever its next life is. So as a mission designer, I want to know, do I have to design for artificial G or not? Right now they're telling me we think we can do it, but we have a couple little data points and they're not for the full 3-year duration.
Yeah. And I think Sergey might argue with you as far as being unfortunate or fortunate. So.
And Misha was with Scott, so that was a crew of 2 for Scott's year long.
Okay.
Yeah, no, actually, great response. Anybody else want to?
Well, so we often kid in our office, and I know these guys share the same scars that I do. We call ourselves the physics police, because that's one of the laws that we just can't change. We can't rewrite the laws of physics. And Mars is a long way off, and it's different than a lunar mission in the fact that the sun is a central body. And so you've got to fly from the Earth, around the sun, to Mars. When you get to Mars, Earth is in the wrong location to come back home. So you have 2 choices. You either brute force it, leave early. As soon as, you want to leave as soon as you get to Mars, you want to leave. And every day you stay, the more energy it takes to come back. And when you return back to Earth, the energy required to slow down is very high. So you either return right away, or you wait until you get back into a good favorable condition and fly a conjunction class mission like Pat talked about. The conjunction class mission is much more lower energy, but it can have some advantages that if your goal is to explore Mars, explore the surface of Mars, then you can shorten up the transits and spend more of the time on the surface, which is less harsh. You've got partial gravity, you've got more radiation protection. So it really, your question kind of gets at the point of what is the critical aspect you're trying to minimize the crew time for. These opposition class missions where you stay just a short period of time are still long. They're at best 500 days, but more typically 600 to 700 days. And so you compare a 700-day mission versus a 1,000-day mission, where in the 1,000-day mission, you're spending 500 days on the surface exploring. That's the kind of debate that you need to have and to really try to understand what is it you're trying to minimize versus what the benefits you're trying to get from your mission.
Yeah.
And then, real quick, from my perspective, it's just the time scale that you look at this. This is my first Humans to Mars conference, but I imagine seeing this in my career, right? So if you were willing to decide today that, hey, human Mars exploration is a mission for your grandchildren, then there are a lot of things you could wait for. But if you're imagining executing this in your career, I think not all the audiences in my range, but close enough. If you want to have this happen in your career, you need to start looking at the capability that exists today to be able to make it happen. And how you will transit in the 40s and 50s could be very different.
And I think I'll just add, on the pragmatic side, we looked at using nuclear thermal propulsion from a budget standpoint just to achieve getting to Mars in the next 20 years. And it more than doubles the human spaceflight budget. It's just a really very expensive capability, while very efficient and very elegant. It happens to be very expensive. So it's and frankly, without money, we're going to be here still talking 20 years from now about what we could do. So the goal is to actually use what we have now as a starting point, and then as we demonstrate we can do this, and as we get the will and the commitment of the people and get more funding, then we can actually move forward and add capabilities as we go on.
Great. So, hey, great question. I'd like to open it back up to questions.
I've been holding off for a couple of days, and it's usually my case to give the first question, but one burning one is, we're going to stay. We can't always depend upon one more Congress and one more allocation and one more appropriation. What role do you see the private sector, and I've seen them on quite a few of these slides, the private sector as having an income stream which makes them a willing partner and participant in the long range, besides a few spin-offs? Is there participation there in looking at how they can make this work for their bottom line?
I don't see a whole lot of volunteers.
I'll volunteer.
I'll start.
Okay, so I did mention that in our current architecture, we're looking at refueling the spacecraft once it comes back from Mars, both xenon and chemical propellants. That becomes a quantity, for the best bidder. I won't say lowest bidder, I'll say the best bidder. We have the same thing. It doesn't matter, what we really need is propellant delivered to the spacecraft in cislunar space. That propellant can come from the moon, it can be shipped from Earth, from an asteroid. That opportunity opens up if you have a basic commodity that's needed. NASA does use a lot of propulsive capabilities in sending people to Mars. So maybe the systems in the spacecraft are done with our industry partners, but there becomes an open market for resupplying them.
So, and I'm not sure I fully appreciate the question, because private industry is involved with pretty much everything NASA does. Are you actually asking if there's a commercial endeavor that it will be self-sustaining without any government funding? Yeah, so that's a tough one, right? 'Cause
I had an answer until you dug the hole that much deeper, right?
all right, good.
So before Rommel digs the hole any deeper, there's a cislunar opportunity that Pat was talking about, but basically, sell services to the government, right, with supplies. Pat was specifically talking about fuel, but that's an commercial venture, if you will, but it's, selling services to the government, not unlike a lot of the other stuff. From a Mars exploration standpoint, at this point, without the ability to have already sent folks there and project that far into the future, kind of see it as a led by nations kind of endeavor, benefit all humanity, noble science, accomplishing noble science goals and that kind of thing. That being the focus at this point, and then.
So a key element of that is, can the United States government or the governments of the world establish stable markets, stable needs that these private entities can then bank on, that from the investment perspective, they're willing to put their own skin in the game because those services or commodities are going to be needed in the future. If we can get to that point, then yeah, Pat and Tony are right. There are certain capabilities and commodities that NASA needs to conduct these missions. So how do you create that stable market that they can then invest in from that?
Okay.
Excuse me.
Oh, well, look at that, we're out of time. Okay, last question.
Okay, right. Could you possibly justify a little bit more this notion of capturing the asteroid, because I've never understood how that helps us for the money that you spend. And if you don't capture the asteroid and you need to double your nuclear thermal propulsion budget, that's certainly a way to get the money to do that. And if you look at what Elon Musk has done with heavy lift, and he's brought things along for a fraction of the cost that you guys have used over the years to develop heavy lift, why aren't you offering prizes to to private industry to give you the capabilities you don't think you can do? If you have to say, I'll double the human spaceflight budget to get nuclear thermal, why leave it at that? Why not go out to the Congress, to the people, and say, look, if you want this capability, here's a prize. We'll give you this prize. You can show us what will do the job, show us prototypes, show us a path, show us all this stuff. These kinds of alternatives never seem to come to your thinking. So how can we go in this direction and get out from under this standard trudging up the hill mentality?
That was a multiple part.
Yes, it was.
I think the Nuclear Regulatory Commission would have something to say about that.
Can I address the benefits of ARM for exploration first? Okay, so my perspective on that mission is what we're doing is between now and the time we want to use solar electric propulsion to go to Mars, that's 10, 14 years, something like that. ARM's going to be our only chance to go up an order of magnitude, go from 4 kilowatts to 40 kilowatts type in-space propulsion to take human class-sized missions on Mars duration-long missions, come back, do all the navigation, test all the systems, test all the reliability. The next system that we build is going to be the full-scale human mission if we're going to Mars in the 2030s. So that's the only chance we have, other than maybe a large-scale deployment of a simulated array, than the timing that we have. So ARM is like is that test mission. It's that it's the shakedown of the solar electric by itself, so that we're confident in it. Because if it doesn't work, if it doesn't achieve the reliability that we need, if there's some issue with it, we still have time to revector to something else like nuclear thermal or all chemical or something like that. So that's the value in ARM to me as a Mars mission planner, is it's going to be the shakedown for an intermediate step in the solar electric propulsion system, the deep space navigation, and the long duration dormancy and ops. Whether it goes to an asteroid, whether they sent it to Phobos, I'm ambivalent towards that. The fact is that they're exercising a human-class solar electric propulsion system before we put humans on it. So that's the ARM question from my perspective.
That's the first half. Real quick,
okay.
The second half of that is the second half of the ARM mission, where it's a pull for advanced suits around a low G body, which we don't currently have experience doing today. And so if you're going to explore the Martian moons and then eventually the Martian surface, you're going to need an advanced suit capability and a place to practice that. So that's, real quick, the other capability that you get from the ARM mission.
So anyway, I think we're getting the hook up here. You all have been a wonderful audience. Thank you, panelists, and have a great evening.